So we're recording. So everything's still given as far as like what to do and the tables and the equations. However, I want to let you kind of maybe take this lab in a little different direction if you want. So I'm going to talk about buoyancy because we would have done fluids on Tuesday, but we moved it up because of the day we lost. So we're actually going to do fluids on next Tuesday. But buoyancy isn't too bad. Buoyancy is actually kind of fun and kind of cool and super easy, to be honest with you. So the idea behind buoyancy is we've talked so much about gravity. We just got done with gravity. And you may think to yourself, well, wait, if everything's subject to gravity, why would a balloon float up in the air? Why does like a styrofoam cup or even you float in a swimming pool? How is it that you're somehow able to defy gravity in a swimming pool, or helium in a balloon defies gravity as it rises in the air? And how this relates to motion is that when you're in a fluid, air is a fluid, all gases are fluids, there's something called buoyancy that can happen. And that's basically because the particle can move around. If something that's less dense than the fluid, it will rise. And that rising is due to a force that causes an acceleration, which causes the object to either go up or down. Conversely, if the object is more dense, it will sink in the fluid. Now, we're going to talk a lot about this in fluids next week. But for us, we're just talking about water. So when you're an object in water, right, you have some water. And let's say I have a sphere in water. It gets pushed up by the buoyancy force of the water. And if it's in equilibrium where it's not going up or down, it has mg and it has fb and the acceleration is 0. So you have this buoyant force that keeps it floating at a certain level. We're going to talk about why that is. So density, I know you all know density. You probably learned it a long time ago. But density, rho, is mass over volume. And therefore mass is rho times volume. We're going to assume constant in everything. And we'll talk about that when we talk about the lab. The other thing I want to tell you is, for us, use the density of water to be 1,000 kilograms per meter cubed. You might have learned 1 gram per centimeter cubed or 1 gram per milliliter as the density of water. When you convert it, you get 1,000 kilograms per meter cubed. And you can convert this if you want. But that is the density of water at 4 degrees Celsius. We're going to assume it's the density of water at all times. So if I take an object and I suspend it from a force gauge, like on the IOLab, so we have some force gauge, and I suspend some mass, right? When I'm in the air, I have a tension up and mg down, and A is 0. So my tension from the string attached to the object gives me the weight of the object in air. We assume that the air isn't giving it a buoyant force. When we put that object underwater, however, still attached to the IOLab, don't put the IOLab underwater, but the object underwater, it now has this buoyant force. And this buoyant force actually, when we do the free body diagram and equation, we get that the tension read by the force gauge is the weight minus. Therefore, this is going to be less when the object's in water because the water is actually pushing it up a little bit. So you weigh less in water. Some of you may have done some kinesiology. One of the things they do to measure the fat content of your body is they'll dunk you in water. And they'll measure your weight in water and figure out how buoyant you are. Which is kind of weird, but so how can we use this? This is all well and good that things weigh less in water. Well, you may know the name Archimedes, but you may not know the story of Archimedes. Archimedes in myth he's a real guy, but I think the story's myth. He was a scientist or philosopher, as they called it. And supposedly the king at the time that he served um, had a gold crown, and he thought the jewelers were ripping him off. So he needed someone to tell him if it was real gold um, without melting it down, because he didn't want to destroy this beautiful crown. And supposedly Archimedes was in the bath, and as he got in the bath, he saw the water spill over, and he suddenly realized what a way to measure if it were gold. And he jumped out of the bath and he yelled "Eureka!" and he ran through the streets naked. That's what makes it a mythical story. However, what he did do is he said that when an object is in water, the amount of water displaced, the weight of that water, meaning the water that moves out of the way for the object to be in the water, that weight of water is equal to the buoyant force acting on the object. So when we look back at this and we say, what is this FB? Well, it's the volume. If I have a cube with some certain volume, when I place it in water, a cube of water of that same exact volume has a certain weight. And whatever the weight of this cube of water, this volume of water is, that is the buoyant force. Remember that we said M was rho V, or rho was M over V. So this is the same as MB, or I mean mg. The nice thing is that the volume of the object and the volume of water are equal. An object takes up the same amount of space as the water. It makes things a lot easier, as we'll see. So the volume of water displaced is equal to the volume of the object. And therefore, when we have this mgvb, remember this is the mass of the object. So this is rho of the object, volume of the object, times g, minus rho of the water, volume of the water, times g, but these volumes are equal. So really what you have is you have Vg times density of the object minus density of water. If if the object is less dense, this tension's a negative, which means it goes up. I know that doesn't seem to make sense, but remember the tension's upward. So if the object is less dense than water, it goes up. If it's greater than water, it pulls down. So we can do 3 experiments with this very simple idea. We could, in air, just out on a desk, we could measure the volume of an object and figure out what its buoyant force should be by assuming the same mass of water that that volume would have, multiplying it by g. We could also use a force gauge, take the object in air, and it would have a tension of mg, and then put it in water, and the tension would be mg minus fb. So if we subtract these 2 tensions, so if we took tension 1 minus tension 2, we would get mg minus mg plus fb, and we would get the buoyant force. So by measuring the tension on a force gauge, where the object's hanging below it, in air, and then submerging it and measuring it again, we could find the buoyant force acting on it. And then lastly, if we could somehow measure the amount of water that the object displaces, we could figure out what the buoyant force is. And we could do that if we could just measure the mass of whatever water spills out when we put an object in it, we could figure out the buoyant force. This is particularly useful. Let's say you have a gold chain or a gold ring at home, and you want to know if it's real gold. Well, if you could put that in water and measure the amount of water that it displaces, like take a cup and fill it to the very rim, put the ring in and measure how much water spills over the side, take the mass of that water and compare it to the density of the object times the volume times g, you could figure out the density of the gold you have and and basically what karat gold is. So what I've done is I've set up this lab. I wrote this lab from an earlier buoyancy lab. And what I had them do was take a roll of like quarters or pennies and put them in a plastic bag and tie them up real good so there's no air. So this was a roll of coins. And then you use a ball, like a toy ball. I used an eraser. But what I want you guys to do is find a sphere, find something round that's big enough to place enough water. But what we're going to do is we're going to take a cup, like a solo cup, like a styrofoam or a plastic cup that you can hang from your iLab. You're going to put the object in there and then fill it with enough water to cover the object and take the object back out. You'll measure it. I'll go over that. But basically, find a sphere, find a rectangle or cube, make them, big enough that they're going to displace enough water to matter. And then something odd shaped. And by odd shaped, I don't know where it went, but it could be anything. It could be a ring. It could be, I used a little pipe fitting that was made of brass. But basically, you just want something that you can't measure the volume. Because what you're going to do is you're going to take a sphere, let's say it's a tennis ball, and you're going to measure the volume. And the volume will be 4/3 pi r cubed. And if you have some kind of little square block, you can measure the length times width times height. And for the cylinder, it's pi r squared times h, where r, and then, so it's a cylinder. I particularly like the roll of coins because you can figure out if they're silver or gold or what they're made of by their density. But it's going to be up to you and your lab group to figure out what objects you want to use. But make sure they're a sphere that's easy to measure the volume, a rectangular cube that's easy to measure, and a cylinder that's easy to measure. They don't have to be coins, although it mentions coins in the lab. So different ideas for objects I've already gone over. The procedure is, number one, experiment one, we're going to measure the volume of the object, and then we're going to use this equation, density of water, 1,000 kilograms per meter cubed, times the volume of the object in meters cubed, times g. And you're going to get a theoretical buoyant force. Then what you're going to do is you're going to take it and you're going to get a big, it can be a huge bucket. It can be a big bowl of water. Hang your object from the iLab with the force gauge on in the air, get the tension, and then submerge it in water and get the tension when it's underwater. Subtract the two, and that'll give you the buoyant force. It goes over this in the lab. The final thing is to measure the mass of water. And this is where things get a little bit tricky. What I would do, so take a cup. I used a styrofoam cup so I could put a hole in it and then attached it with floss to the force gauge on the iLab so that I could measure the weight. But however you can attach it so that you can measure the weight of it on the force gauge, then put your object in it, fill up the water so that it just barely covers your object, and then remove the object and try not to let too much water leave with the object, right? You don't want to use a sponge and try to let all the water shake off into the cup. But when it's submerged, draw a line, draw a thick line on the cup, which is why a cup helps. Once you take the object out, the water level is going to drop a little bit. Measure the cup with the water level after it dropped below the line. Then refill the cup to that line. So you're basically adding enough water to fill in where the volume of the object was, and then measure it again. And the change in mass, so the mass when it's full minus the mass where it had fallen after you pulled the object out, that'll give you the mass of the water that the object displaced. And the mass of that water times g is your buoyant force. So what you'll do is you'll have, in effect, you'll have a theoretical, which is from, density of water times the volume of the object measured, that you measured with like a ruler, times G, and this will be your theoretical. You'll have a buoyant force that is the difference in the two tensions. And then you'll have a buoyant force, which is the mass of the water times G. And you're going to compare these two experimental buoyant forces to that buoyant force. That's what we're going to do. Now, obviously, there's going to be a lot of chances of error here for weird reasons. Number one, we're going to assume that, oh, and when you submerge your, when you do the bowl, don't let it touch the bottom. Make sure it's suspended in the water and make sure there's no air bubbles. We'll talk about that later. But what we're doing is we're seeing if Archimedes is right. Is the buoyant force equal to the volume of the water displaced times the density of water times G? And we're doing it two ways, but we needed a theoretical value. Now, you might have something weird going on. I had students that were doing it that didn't realize there was water getting in. They were using like an Altoids tin for their cube, and water was getting into it while they had it underwater slowly, and it messed up their numbers. So hopefully that doesn't happen. But here, you can see that on the data tables, you're going to get the volume of whatever you have. If it's a cylinder, great. And then weigh each one. And this is done the same way that we did when we were measuring the IO lab. Basically just hang it with floss, if you can. Get that mean, get the standard deviation, the sample rate, the time interval, and exactly what we did on our lab that's due today, so that you can do the error analysis on it. And then do the same thing when they're submerged, and then do the water displaced. Okay, so now this actually is kind of off. This should be the weight of the water displaced, meaning when you take the object out, how much water is in there. And then this is the water when you filled it back up. So you're going to subtract this water from this water. But everything's done for you, everything's shown for you. It shouldn't be too hard, and everything you need is here. And then on the data table, as you go down this data table, this is the measured volume using a ruler. This is the mass using the IO lab. This is the density, which is the mass divided by the volume. This is the tension force when it's in air. This is the tension force when it's in water. This is the theoretical buoyancy force. And sorry, this is from the tensions. This is from the change in waters. That's not air and water. This is the theoretical buoyancy force, and then the percent differences and the percent errors. Okay, so on to questions. We don't want air bubbles, and we don't want them touching the bottom, because air bubbles take up extra room, and they'll give you a inaccurate density for your object. They basically, take up more volume of water, so it looks like more water was displaced than actual. If it's resting on the bottom, you'll have a normal force that's actually reducing the weight of the object too. What's heavier, equal volumes of ice or water? That's a little tricky. Heavier, what does heavier mean? I think they mean what weighs, or what has a bigger mg or a more buoyant force. That's really up to you to answer what heavier means to you. But I will say that ice is much less dense and it takes up more volume. That's why it's less dense, obviously, than just water. So Ice is less dense, meaning it's lighter, if you want to call it that. And then if you do use coins, if you don't use coins, just let's say you have a rubber ball, look up the density of rubber and see how it compares. The nice thing about coins is we also a lot of times we think pennies are made of copper or quarters are made of silver, and you'll find that the density doesn't match, which is a little weird. Um, Not really, because for a long time the government has cut our coins. The amount of copper in the coin is cut with nickel and other metals because copper is precious and silver is precious. So they kind of code it, but independent variables are the ones we set in this. That would be the objects, to be honest. The fixed variable is gravity. It's the only thing we can't change. Density of water, I guess, is the other one. And then our dependent variables will be the tensions or the masses, basically anything we're recording on the force gauges. And then in the conclusion, just state whether you, make sure you state whether Archimedes' principle is true based on your experiment. As always, how accurate your data, what are your percent error, percent differences, what do you think causes error? Now, it's going to be hard to get all the water. It's going to be hard to get the water level correct unless you're really, really good and using like, you know, chemistry glass, you know, that's measured, perfect measuring stuff. But if you can think of a way to make this experiment or to come up with a buoyancy experiment that might be cool, let me know in the conclusion. So everything's here for you. I hope that you won't have too much of a problem figuring out how to do this. Since it's all stuff we've done before, and it looks hard, but it's actually pretty easy when you do it in when you get down to it. And I want to give you guys a little bit of room to be creative and find cool objects. It says sphere, but if you can find something kind of cool that's round enough for you to measure the volume of, great. Something square, something that's a cylinder. If you want to measure your girlfriend's gold necklace and figure out what the density of it is, that'd be cool. Let me know about it. Let me know that you did the experiment. So yeah, have fun with this one. Our final lab is actually not next week because next week's Thanksgiving. It's the week after. That lab we're going to do in class. It's like a worksheet that we're going to do in class. And I'm going to go through every part of it with you. It's on periodic motion, basically taking the motion of the IOLab going up and down on a spring and turning that into a sine wave and being able to read what the periodic motion of the sine wave is. So it's more of a worksheet handout than a lab next week or 2 weeks from today. Okay, so any questions on this lab? And as always, I know a bunch of you have been asking me questions about the lab that's due today. You can always do that this week too. I know you asked me that privately, and I don't mean to put you on the spot, Ahmed. For those of you who are here that came late, if you're unhappy with your lab grade, what I want you to do is do your best to be prepared for the final. As far as your grade's concerned, don't worry about your grade right now. I know you're worried about your grade, but here's the thing that I promise you. If you've done every exam and you've done all your labs and you've really got most of your homework in, I'm not going to fail you. I'm not going to give you a D. You're going to pass the class, but you may not pass it with the grade you want. However, the most important thing is getting all your work done, doing all your work. And I'm going to take that into consideration when I'm figuring out your grade. Is all your work in, or are you getting, you know, a horrible grade because you're just not turning anything in? You're not, you know, doing a good job on labs. You're not doing any of your homework. I need to warn all of you, your homework and your lab grades, if I don't put in a 0, Canvas treats it like it's not there, which means if you only did one homework assignment, even though we're on number 13, if I don't put zeros in for the ones you missed, Canvas might say you have 100% on your homework, and you don't. You have one homework in out of those. That being said, if you're really super worried about your grade, we can talk about it in the next week or two. I would rather do it after Thanksgiving, but we can talk. We can see what you need to do, where you're at. We can have a Zoom meeting and go over your grade and see what you need to do to get where you want to be and what's actually achievable, depending on how well you did on the final. The final, though, is easier than what we've done so far. The final, I think, is the easiest exam, to be honest with you, because fluids and gravity and periodic motion aren't super hard. They're all different, and they're all easy to recognize what you should do to solve the problems. So there won't be, but that doesn't mean that if your grade was horrible, that you, I don't want you giving up on the class. I don't want you thinking, oh, well, I'm screwed. I'm going to get a bad grade. If you really want to talk to me about it, we can talk, but let's do it after Thanksgiving. Look over your grades, figure out what you're missing, what you need to turn in. If you're missing homework assignments, how much of a difference they'll make on your, total grade right now. And then talk to me and we'll see what we can do about it. My goal is to make sure that you understand 4A before you get to 4B. I've got to give you the tools so that you can be successful, because if you go into 4B not knowing what you're doing, you are going to fail out so quick, it's not even going to be funny. So if you're having issues, we got to talk and we got to get you straightened out by the final. And we'll worry about your grade at that point. Okay. And I know that's kind of hard when you do bad on a test, but just know you're not going to fail. If you hang on and you keep working at it, you're not going to fail. Okay. Other than that, read through this lab, get with your lab partners, come up with some ideas for objects that you think you would like to use. If you don't have any ideas, use what I said: a ball, an eraser, a cylinder of coins wrapped in like a plastic bag, really airtight, and then some weird odd shaped thing. It could be an earring, it could be, I don't know. It needs to be big enough that you can displace enough water. But other than that, I'm done for the day. I don't have anything more to tell you. We'll go over homework 13 next week too, and go through those gravity problems after we do fluids. So if you're doing the homework this weekend and you're struggling with it a little bit, we'll go through it. We're going to have a quiz on elliptical orbits. So that's one section of chapter 13. Make sure you know how to do like the Mars example that was in the lecture. Make sure you know how to do an example of finding like the eccentricity if you're given the aphelion and perihelion distance, and finding maybe the period or something like that, the velocity at aphelion or perihelion. It won't be hard if you know how to do it, if you do an example. If you don't, you might do horrible on the quiz. And there are 2 or 3 of those types of problems in the homework, where you need to figure out the orbit of an object and you're given perihelion or aphelion or eccentricity or period. Okay. Other than that, I'm done. I'm going to stop recording, and I will see you guys on Tuesday.